Okay, so welcome to today's video. We're going to cover mesh analysis, and the idea is that we're going to just practice about 4 problems to get you the hang of things. In the previous videos, I went over the actual approach to mesh. I'm going to condense it now to just really give you some practice. Obviously, the more practice you do, the better, and hopefully the more comfortable you become. So first, of course, is going over the basic procedure that we talked about before. I'm going to use clockwise notation for mesh. I'm going to label my mesh currents, write our KVL equations for each loop, and then we solve. And as far as simplicity, because we're going clockwise, I'm going to be using the positive for currents entering into any resistors to simplify our process. So when we go ahead and get started, so here's our circuit. We have 2 voltage sources here, 28 volts and 7 volts. And of course, we know by default the polarity of it because that's given to us. And if you're not unfamiliar, again, the smaller end of our voltage source is going to be negative. The larger this top bar will be a positive end. And now we're going to determine the direction. As I mentioned in step 1, we're going to be using clockwise. I'm going to go around clockwise for each of these loops. I'm going to write give it a label on mesh currents I1 and I2. I'm going to write down my KVL equation. I'm going to also enter my positives for my resistors entering, and I'm going to solve. So let's do this together so you can see how this is all done. So again, for my resistors, I'm going clockwise. I'm going positive, negative. On this side of the resistor, positive, right, negative, right? And how this loop looks like for my current, it's going to be going clockwise. I'm going to give it a name. I'm going to call this loop here I1. I'm going to call this other loop here I2. And of I2, on this second loop, again, on this side of the 2 ohm resistor, be positive, so I'm entering into that branch as mentioned in step 4. And mentioned step 4 again, positive, negative, and the voltage source, we can't change it because whatever it's given is that positive sign. The next thing I'm going to do is I'm going to now try to give it a label. So I'm going to go around this here, call this A, B, C, D, so you can have an idea of the corners. But say if I call this corner here A, I generally like to start in the far left bottom corner to get myself comfortable with setting this up. And when I write down my KVL equation, I like to label everything. So I'll call my first one here loop number 1. And with loop 1, I'm trying to sum up all the voltages, and it's going to be equals to 0 volts. And that's what Kirchoff's virtuous law is getting at. So if I'm going to read everything that's entering into each of our components. My first component, if I start from A, is entering to the negative terminal of the 28 volts, the positive terminal of the 4 ohms, positive of the 2 ohms, and then I've completed that loop. So that the map equation for that, or the voltages for all that, will be the following. It'll be read as minus 28 volts plus 4 times it by I1 plus 2, right? And it's 2 ohms. Because I am in loop 1, it's going to be I1, and it's opposing the direction of I2. And all of that will sum up to be equals to be 0. All right, so that's how you write the first KVL equation. And again, if you'd like to get a little more details on the particular portion of it, which if you're new to the channel will be this one over here, this takes into account the counteraction of the 2 current sources that are affecting the 2 ohm resistor, and it looks like this. So a quick idea of it again is that the 2 ohm resistor in the center is experiencing current that's taking into account I1's direction, and then it's being opposed by I2's current flow. Okay, so that's what that actually happens. And again, I go over that in another video. So now I can simplify my equation here. So when I simplify it, which means I'm just trying to put all my like terms together. So 4 and 1 gives me back the 6I1. Then we're going to have here minus 2I2, right? Then I have the minus 28 volts. I'm going to move that to the right hand side of my equation to get back my 28 volts for my equation number 1. And I therefore was able to simplify my problem. So I just boxed that to make it convenient so I can see how I did that. Because now we're going to use that knowledge to solve. Then we'll repeat this process for the second loop. So I'm going to write my loop 2 equation. Okay, and again, same strategy as before, nothing changes. It's still going to be the sum of all my voltages will still equal to 0. I like to start from edges of my boxes. So if I use this again, right? With the blue edges. And I'm going to go from the far left bottom blue edge and go around clockwise because I'm using clockwise notation. And to read that off, it's going to hopefully be not too bad. So I'm just copy and paste this actually, so it's a little bit more easier for you to see. And copy that and paste it over here. It's a little more simple. And now if I read that, and I'm going to now call this side here A, B, C, D again, just for convenience so you can get an idea of how I'm doing this. I'm starting from that corner A. It's going to be read as, and in here, notice now I'm on the right side of this loop, the positive terminal is there. So with that there, I'm going to read as 2, and I'm in the second loop, so we have 2 times I2, and what's opposing that flow is I1's mesh current plus 1 I2 plus 7 volts equals 0. Okay, so I do what I did before, just simplify this to try to reduce it. And so with this 2 I2 minus 2 I1 plus 1 I2 plus 7 volts equals 0. So I have here my two like terms. I'm going to just simplify that. So when I simplify it, I'm left with this. And I'm left with this simplified equation. And ultimately the problem is kind of done, so it's not terribly bad. So I'm going to put them together so you can see them. I'm going to copy and paste this. Okay. And what you're hopefully observing is something important. And that importance here is that I'm going to have here 2 equations, and the idea is I'm going to have 2 unknowns. Okay, so there it is. So let's try to write this all out so it's more clear. So I put my line to separate here. This is going to be my equation 1 that we showed before. This is my equation 2. Okay, and the goal now is to try to solve this in hopefully a reasonable fashion. So the one thing that we can do is that we can try to come up with a mathematical approach to solve for this 2 equations, 2 unknowns. But hopefully we can look at this and have a clever way of solving it. One of the ways that we can do this is that we can take this and we can sum up equation 1 and equation 2 and hope that something cancels out. By default, you see that nothing really cancels out right away. However, if we do the following to it, as you learn in your math classes, say if I now multiply both sides of the equation by 3, right? I'm going to be left with the following. So let me just copy and paste this so you can see it all. So here's what we're going to be left with. So if I distribute out this 3, I'm going to be left with minus 6 I1, right? Then we have here minus 9 I2 equals to minus 21 volts. Okay, so that's the first step. And why am I doing that is the important part. So the y comes down to the following. So if I'm combining these 2 equations, okay, so what I have here, let me just also move this a little bit further so it's a little less distracting from the previous screen. What's important is that the positive 6 and the minus 6 cancels out, right? So algebraically, what I'll have left, I have a negative 2i2 and a negative 9i2 becomes my minus 11i2. And that's going to equals to a positive 7 volts. All right, so now we have some sort of relationship between the two. Yeah. So correction on that, this is actually a positive sign. I need something that looks a little bit weird, but this is actually a positive 9, as you can see from over here, that this becomes a positive 9. So I take that back. This is actually coming out to be positive 7 I2 equals to 7 volts. So therefore I2 is going to equals to 7 volts over 7 ohms, right? So I2 equals to 1 amp. Just like that, we're able to solve. Straightforward. So we get back 1 amp equals to my current in my I1 loop. All right, so that wasn't too bad. So now in order to solve for the current 1, we just have to plug in I2 into either this equation, of course, or this one over here. So let's go ahead and try that out. So if we do that, we're going to be left with the, say if we use the top equation, let the 6I1 minus the 2I2 equals to 28 volts. I plug in my value of I2 and I get back 6I1 minus 2 volts, right? So I'm going to, if I substitute in the 1 amp and I multiply by 2 ohms, I get back 2 volts, right? Equals to 28 volts. So now, if we now solve for I1, we're going to move over the 2 volts to the right hand side. And what we're going to end up with 30 volts will equals to 6I1. Therefore, what we end up having is I1 will equals to 5 amps. Okay. And again, that's going to be because I1 will equals to 30 volts over 6 ohms, right? So 30 over 6 gives us back the 5 amps that we're looking for this problem. Okay, so we can do a quick check on this to make sure that we're doing everything right. So our solution for I1 is 5 amps. Our solution for I2 was the 1 amp. So if we were now to do a check, we just copy and paste this so I don't lose track of everything. So I'm going to copy and I'm going to paste it over here, and I'm going to copy this one as well so I keep track of all my steps. And that always comes in handy that you can continuously repeat and write down things multiple times to get the hang of it quickly. So here are my 2 options, and with my check I can literally put back in my values of 5 amps on my problem set, and I can also put in my values of 1 amp as well. So let's take a look at that in a little more detail to see what I mean. So if I now copy and paste this, see if I do this okay. So here it is. So put that in there. What we can certainly do is now we can put in our values of I1 is 5 amps, and then if we have a 4 ohm resistor right here, so I multiply 5 times 4 to get me back 20 volts, right? That's going across the branch, as I mentioned before. And by the way, my values for I1 and I2 are both positive, which means that the currents are going clockwise. Again, I'll say it because it's very important. Because they're positive, the 5 amps is going this way, it's going clockwise, and the 1 amp is going clockwise as well, which is really important to us. And remember that if my value for I1 was negative 5 amps, that just means that my current is going counterclockwise, which is important pictorially and helps us understand the middle branch, but we'll go into that with the next problems. Okay, so now we see that we have 20 volts there. So now if I put in for I2 and I put in my 1 amp over here, and I multiply my 1 amp by 1 ohm, right, I get back 1 volt across this resistor. Okay, so I'm going to draw this problem for you slightly differently because hopefully this will help you see something that's really important. So take a look at this. So here I am. I'm going to draw it in this variation of my problem. And in a previous video, I hopefully explained why this is so critical to our understanding. So if we do it like this, and I'm drawing it this way, the first reason why I'm drawing it this way because it helps me identify the node a little bit more clearly, and then it hopefully will help us understand how each branch behaves a little bit better than this previous picture does. So what do I mean by that? So putting in my positive and negative signs everywhere so you're familiar with how this would be read. And here are my sign convention on all of my sources and all of my resistors, right? So here it is. Put positive and negative on the left side because I'm safe. I'm looking at this from I1 standpoint. This is how it looks like. So step 1, of course, is to recognize that for parallel, right, we hopefully learn that the voltages are the same in each branch. So let's see if that holds true of our understanding for our check. So remember what I said over here, that if I did 5 amps and I multiply it by 4 ohms, I get back 20 volts. So my question for you as you start to look at these problems is to figure out that I have a top node, right? This is my top node. And then here I have my ground node, or my reference node, or my node 0, depending on your textbook, right? So those are the two nodes. And what that means is that there's a potential difference from the top node to the bottom node, okay? And what we're expecting is that all of the voltages across each branch will be the same. So from this diagram, if I start from my bottom node and go up, I can read it in the following way. It's going to go from the ground node. I'm going to enter into the negative terminal first, so it'll be minus 28 volts. Then I go up. I'm entering to the positive terminal of the resistor. And then that voltage, because that's 4 ohms times it by the 5 amps, gives us back for that branch a net of minus 8 volts. And again, that's if I'm reading it from the bottom, from the ground up. If I'm reading it the other way, I could technically also read it from the node to the ground. As long as you're consistent with all 3 branches, you should get the same answer. At least the positive negative polarity, the potential difference between each 3. So if I did that, I'll get that. So this is for the right branch, okay? And now by inspection, if I do the same so it would be great if I knew between my left and my right. That's my left actually. So if I look at my left branch, I get back minus 8. So now if I look at my right branch, we can hopefully look at that as well. And remember that the right branch, that this is 1 ohms, and I've multiplied 1 ohms by the 1 amp that we solved for. This means that there's a net of 1 volt there. Right? So if I start from the ground, it's read as minus 7 volts plus minus 1 volt equals to minus 8 volts, which is pretty exciting. Okay, so now we're showing that the voltages are the same for the branches, right? It's going to be our backhanded excitement to solving this problem. And what we expect now for the middle branch, right, is that what we know is that we expect that should also be 8 volts, right? Hopefully our instincts tell us that, because again, for parallel branches, the voltages are the same everywhere. So for that branch, we should also anticipate that to be 8 volts, positive or negative, depending on how you're visualizing this. And what we noted from before is that should be the case. And how is that possible? Well, if we look at our equations for I1, our loop 1 equation or our loop 2 equation, recall that this was our loop 1 equation, for example, right? Here's our loop 1 equation over here, and our loop 2 equation is the second one. So I'll just copy and paste it from here. It's just a little more easier for me to do that. So I copy and paste it, and I put that here. And this is a simplified version, right? But if I look at the full version of the problem, which is a little more important for this case, and hopefully you recognize why. So here's the full variation of loop 1's problem, right? So I'm going to put that here. And what that means for us, so let's put loop 1, is that we see that from loop 1 is that there's 3 terms. The first one is the voltage source, right? Here's the independent resistor that's not attached to anything. But here's a definition of our current that is now going across the 2 ohm resistor. So what does that mean from the node standpoint? Well, from the node standpoint, it's going to look like this. We've identified that if we go clockwise, right, and here's my node. First, let me draw my node for you. And that node means the top branch, and here's where the 2 ohms is going to be, right? So you can get a visual of how that looks like. Let me just delete that, put it a little bit better so it looks a little more neat like this. So now you have, and remember what we solved for, because they both are positive, that means they both are going clockwise. It's got 5 amps and 1 amp. So there's 5 amps entering that node, 1 amp leaving that node. And because our value was positive, negative on the terminal, right? And if I'm investigating that from loop 1 standpoint, it would be that according to this node, the current, we expect it to go in this downward direction, right? It's very important, and hopefully you're getting the idea of it. So in other words, what that means is that my sums of all my currents entering that node will equal to all the sums of my currents leaving that node. So I have a 5 amps that's entering that node will equals to the 1 amp plus some unknown amp. And the only way to get that current that's going through there, that must be 4 amps, right? So because it must be 4 amps, and we could have also solved that even easier, we could have also said by default that over here, our value of the current across that branch must be our 5 amps subtracted from our 1 amp, gives us 4 amps as well. This is the visual representation of what this is trying to tell us, okay? It's really important. If you see that now, it's going to help when we get to more complicated circuits. So now we know that we're going to get back 4 amps going across that branch. And that 4 amps signifies that over here, that this is going to be 4 amps. So if I'm reading it from the ground up, it's going to be 4 amps times by the 2 ohms will give us back the minus 8 volts. So again, it's going to be 2 ohms, multiply it by the 4 amps. This give us back, if I'm reading it from the ground standpoint, it's read as minus 8. And if I'm going from the node to top down, it's positive. But again, all dependent on how you're used to observing these problems, either or form is fine. And you should be satisfied with noticing that our solutions make sense. Okay, so think about that, and hopefully this is starting to be a little bit more clear on how the approach would work and how we would approach it. And again, the minus 8, minus 8, minus 8, you could have also thought of it from the top node down. And if you did, it's the same, right? So then you would be left with the 8 volts, 8 volts, and 8 volts. To solve for it, perhaps with this problem, it might make more sense to use it from that direction, from the node down. But ultimately, it's just a potential difference, right? So depending on how you want to perceive the problem, either or perceptions of the problem are fine, depending on what your professor is asking or the textbook is asking for you to solve. All right. Okay, so hopefully that makes some sense. So let's go ahead and look at another problem. And the other problem over here, if I can get to it. Wow. Okay, so here's the other problem, and the idea of that is the same. So you're going to do what we did before, and again, this is just a practice day to get you comfortable solving these problems. We're going to do here, going to go clockwise again, give it a name, I1, say this one's I2. For this first one over here, I'll start by, labeling it kind of how I did before, but eventually you're going to be using, you won't have to write all these steps every single time until you get comfortable with it. But the idea is that this is how I'm approaching it. I'm approaching it from coordinate A always, or 98% of the time. So I'm going to read this as minus, I can write the pen here, minus 7 volts plus 1 times it by I1, because there's the 1 ohm resistor is not affected by any other current source, but just that mesh current, plus 2, and I'm in loop 1, I1 minus I2, plus 6 volts equals 0. Just like that, I wrote down my loop number 1 equation, and then this is, of course, doing my KVL for each. Then I simplify and I solve, right? So these are the 2 current sources that I have. Here are the 2 voltage sources that I have. So I get minus 7 and positive 6 gives me back negative 1. Move that over to the right hand side, I get 1 volt. And certainly now that I have the 2 I1, and the 1 I1 gives me back the 3 I1. And then I have here minus 2 I2 equals to 1 volt, right? So again, it's just simplifying this hopefully relatively quickly, and then we can solve. I repeat this problem again, and this time I'm going to do the equation from loops number 2 standpoint. So if I go to loop number 2, I do what I did before. Here's I2, here's I1 again, right? And this time I'm going to, again, for sake of you guys getting comfortable with it, this is the strategy again. I'm doing A, B, C, D as I go around this, and I'm doing what I did before, writing my KVL. So to keep it organized, do loop number 2. Sum of all the voltages will equal 0. If I start from A, it's being read as minus 6 volts plus 2. I'm in loop 2, so it's I2 minus I1 plus 3I2 plus 4I2 plus 9 volts equals 0. Okay, so there's that whole thing. So to simplify it again, and hopefully I don't make any algebra mistakes, but I have several I2s now. So here are the 3 I2s, and of course I have my voltages here, so I keep track of all that. So if I distribute this out, hopefully I can do this right, minus 2I1, 2I2 plus 3I2 plus 4I2, 7, that gives me back 9I2 plus 9I2, and then I have a minus 6 and a positive 3 gives me back a minus 6 and a positive 9 volts gives back a positive 3 volts. Move that positive 3 over, I get back a minus 3 volts. And that is what I have for my reduction of my second equation. And just like that, I'm ready to solve, right? So not too bad so far. So here's my two equations. So I'm going to then group them together to have everything organized to solve. So grouping them, here I'm going to copy and paste. So here's how it looks like. So here's number 1. I'm going to copy that, place this over here, and let me just delete this to make it so clear. And then certainly I'm going to do that again here. And now the important stuff is to make sure we stay organized, which is the hardest part of solving anything circuits related, is to try to remain as neat as possible. Hard thing to do, especially when you're in a rush or timed on an exam. And then I try to label it here as well. So I put here, for example, EQ1 and EQ2, representing equation 1 and equation 2 respectively. Okay, so now that I have that there, we can use the same technique that we did earlier. And what that technique was trying to state is trying to simplify this and only have one unknown left. So a strategy on this is that I have nothing directly that cancels out. However, if I take this, and let me just put it over here so you can see it again. I'm going to duplicate that for you. So the idea is that I'm going to try to sum these up. So if I sum these up, right? If I did this outright, I'm still going to be left with one equation and one unknown. So I'm trying to simplify this. So let's say if I try to eliminate the I1 first. So if I try to remove the I1, I can do the following. I can use any math technique, but this one might make sense. Multiply the first one by 2, 2 on the left, 2 on the right. Then I multiply the second equation by 3, 3 on the left, 3 on the right. And that hopefully brings me down to something nice and simple. So I'm going to distribute out the 2 for the top one. And if I distribute that, I'm going to be left with 6I1 minus 4I2 equals to 2 volts. Then I distribute the second equation, EQ2, and we left with minus 6I1. Then you have here plus 27I2 equals to minus 9 volts. Okay, so just like that, we're able to set our equation up to hopefully make it to simplify it. If I combine them, my I1's now term drops out. I combine 6I1 plus negative 6I1, that creates this to 0, right? And then I'm going to have here 0 minus 2I2, sorry, if I can read my own handwriting, what did I do there? Oh yeah, so I'm going to have here, when my algebra mistakes are just terrible today, I'm rushing. So I have 18, 3 times 9, right? So if we did that, I was right the first time. So if we did that here, we can now simplify and then we can try to solve. So let's go ahead and simplify that. So simplification, you're left with here, what is this? You're left back with a positive 23, right? I2, and that's going to be 2 and a minus 9, give me back a minus 7 volts, right? So we can get back that I2 is going to equals to minus 7 volts over 23 ohms. And we finally get back an answer. So let's go ahead and type that out. So if we do that, we get a number of minus 0.304 amps. Okay, so that's going to be our current for I2. So that's really important. So I'm going to highlight this for a quick moment because it's going to come back and I have to show you this graphically what this means. All right, so that's what we get for I2. And now since we know I2, then we can solve for I1. So what we're going to do next is that we're going to take our value of I2 and then we're going to plug it back into either of these equations. We should get back a value for I1. So if we plug I2 back into equation 2 or equation 1, we should get something of interest. So let's see here. So say if I did this, if I did 6I1 minus 4I2 equals to 2 volts, and I plug in minus 4 times it by minus 0.304, and it's again, I'm rounding a little bit, 2 volts. And then 6I1. It's going to punch this all into my calculator for you. So we can see what we get. So we get back this 1.216, right? And then that's going to be positive 6I1 equals to 2B. And then I'm going to do that. Let's see here. Sorry, I was punching in all these numbers for you. So we're going to get back here the 0.784 volts, which equals to 6I1. And then we go ahead and we solve for I1 in this case. All right. And after punching in, I get back my values. I1 equals to 0.130 repeating, no, 0.6 repeating amps. Okay, so that's what we get back for values of I1. Now for a check, what we'll do is that we'll substitute back in our values I1 and I2. So I went ahead and did that for you to save a little bit of time. So to substitute those values of I1, let's copy this and put it a little bit closer so you can see. So here we had a value of I1 to 0.1306666. So it keeps repeating after that. So I didn't include that, but kindly do that with your own calculator. You can see how that affects the proof in a moment. And what we're going to do is that we're going to go ahead and grab any of the loop 1 or loop 2 main equations. So if I grab loop 1's equation, so here's loop 1 equation over here, and I now substitute in my values of the 0.130 into I1, right, times 1 ohm times it by 0.131 gives me a voltage for both combined. Now we realize that I1 minus I2, right, it's the current that's going across this branch, and the 2 ohms here. So as a check, you'll see you'll have 0.130 minus a negative 0.304 times by 2 is the voltage across that 2 ohm resistor. Combining a 0.3 and the minus negative 0.304, it gives you back 0.434. Multiply it by 2. The negative 7 and the positive 6 gives you negative 1 volts. Move it to the right hand side because it's 1 volt. And I combine the 2 times it by the 4.34 plus the 0.130. And I get back, again, because I rounded, 0.998 volts, which is essentially 1. If I put this to 8 or 9 significant figures, it certainly will come back to be 1 volt. But for the sake of time, let's call those both 1. We'll take that and move on from there. Okay, so now problem 3 is a little intriguing. So if you look at this problem at first glance, you might look at this and say, you know what? This is going to be a 3-mesh or 3-loop equation. And technically, yes, you're correct. You can do that, right? So let's just show you what I mean by that. We could certainly say to ourselves that we're going to identify all these here, and then we're going to call this one loop 1, loop 2, loop 3, call this I1, I2, and I3, and try to solve this. Remember, if you do 3 loops, that's essentially going to mean 3 equations or potentially 3 unknowns. So you're doing a 3 by 3 type of problem. And that's no problem, right? That's something that you should be able to solve with someone, folks of your caliber. If you have any math, algebra background, this is hopefully not too big of a deal. But in a case like this, where if you look at it carefully, you'll notice that the 20 ohms is directly in parallel with the 5 ohms, right, is that you could essentially simplify this entire circuit into a two mesh problem. Okay, so I'm putting problem number 3 just as an identifier problem. So if you see something like this, you can either do it the long way, which is trying to do it like this, or we can simplify it. Okay, and what do I mean by simplify it? So let's try it together, and then we're going to see if we can simplify this problem and solve. So let me go ahead and copy that, and we'll try it over here again. Let me do that one more time. That came out not as perfect as I was like, of course. So if I try to do that, okay, so and I try to put this problem here, what we can do is that we can now take this problem and we can do something like this, right? So I'm gonna duplicate this one more time just for the fun. And then what we can do now is that we can say that this resistor, and I can call this new branch here R. Just temporarily call it RZ because it sounds great. And I can call RZ equals to the 20 ohm resistor in parallel with the 5 ohm resistor, right? Is what I could potentially do. And then I could simplify that. I could simplify it one more time. I can do it a third time, say, and maybe make it like this. So let me write it as this. I'm going to duplicate this one more time, and I could perhaps simplify this, and I'll call this one here, let's say, I don't know, running out of variable names. We'll just delete some stuff so you can see it more clearly. So I could simplify it again, where maybe I'll call this R X, I guess, and that's going to equals to RZ plus the 8 ohms, right? Resistor is what I could simplify this to become. All right, so think about what I just did there, and then of course this is going to be the equals equivalent to the 20 ohms in parallel with the 5 ohms plus 8 is what we expect our new temper resistor Rx to be. All right, so let's try to do that together and see if we can take this problem that looks like a long, complicated problem and simplify it something a little bit easier. So in order to do that, let's do what I just stated. So let's first do this piece of the problem. And if we did that, we're going to be left with the following here. So if I wanted to figure out what is my 20 by 5 going to be equals to, so we know that RZ is going to equals to 1 over 1 over 20 plus 1 over 5. Or I can also say that RZ will equals to product over sum, which is much faster, which is the same thing, which is going to be 20 ohms times it by the 5 ohms over 20 plus 5. All right, so you're going to have here 100 over 25. So my RZ will equals to 4 ohms, right? So now that I have the 4 ohms, let me sketch this variation of the problem for you. So it's going to look like this. Duplicate again. So it's going to look like that. And let me replace this here. And this is going to be 4 ohms over here. And finally, to have the true form of the problem, let me copy this one more time. My Rx variation of this. This time I use copy. And then what we're going to be left with is that we're going to be left with the 8 plus the 4. And that gives us back our 12 ohms to be our final value for that branch. Okay. And then realistically, we just repeat exactly how we did the previous two problems. So it's not terribly hard, right? So you're going to go ahead and do the minus 9 volts plus the 5, 6, and do the same. So I'm going to quickly pause and solve this so it can save you some time, and then we'll get back to the final problem. Okay, so if we wanted to do a quick check to see if we're actually correct, we certainly can just go ahead and revisit the problem that we have. And if you look at our loop 1 and our loop 2 equations that we solved for before, right? Sorry, take that back. So in order to solve this problem, and we go ahead and write our loop 1 and loop 2 equations, what we're going to end up with is that we're going to end up with this We're going to start from this corner again, go clockwise around. So we have minus 9 volts plus 5i1 plus 6i1 minus i2 equals to 0. Here's that equation simplified. You get 11i1 minus 6i2 equals 9 volts. Repeat that for our loop number 2. You get back, I'm starting at this corner again. So I'm left of 6 times by i2, I'm in loop 2, minus i1 plus 12i2, right? Minus 9 volts equals to 0. Finally, I simplify that to this form over here. Okay, I put both of those equations together, so I put them into this form over here, so I have the both equations. And notice here, if I try to combine them outright, I'm going to still end up with two unknowns. We have what is this, 5i1, and here you would have the 12i2 equals to 18 volts. So it doesn't really get you anywhere. You're still going to end up with one equation of two unknowns, which is not helpful, which means that if we found a way to simplify this, if I multiplied, for example, the top one by 3, the left and the right side by 3, I'm going to be left with this 33i1 minus 18i2 equals to 27 volts. And then now you notice that the minus 18 and the positive i2 cancel out. So I'm left with a combined of 27i1 equals to 36. Therefore, my i1 is, algebraically comes out to be 1.3 amps repeating, 1.333 repeating. Same again if I did i2s and I take my value of i1 and I plug it into either this equation or this equation, doesn't matter which one you choose. What I end up doing, I plug it in, I solve, I get back i2 equals to 0.944 amps. Okay, so just like that, you can do this problem and condense it. So some of you are probably wondering, well, what if you're asked not for the current of I1 or I2? What if you are now asked from the original problem, because you know, no one's going to give you problems that are simple all the time. They want to know the current through the 20 ohm resistor. Okay, so say that that's the actual question to this problem. So in order to solve that, I'm going to copy and paste this again. So here it is. Okay, and let's think about what our answers came out to be. All right, so let me actually put all of them here so you can see this graphically in multiple forms, because what I'm getting at is all three graphics that I drew are equivalent to each other. So here is another representation of what we just solved for. I'm going to put this here as well. So I'm going to put paste, and let me do the third one too, the final one, so you can see the middle variation of this as well, and we can hopefully get the big picture across of why this is interesting. And let's see if I can find that image, of course. So that image, you know what, I'm going to copy both of them. I think I may have ventured a little bit too far, so I put them both over here for a brief moment. Okay, so here it is. So let me slide this one over so that we can see the logic of this. You know what? Let me put it this way. Okay, so now we have all three variations of the problem. I'm going to remove the stuff that's unnecessary for now. Remove this too. And now we have all three steps. And what I'm trying to say, which is critical, is that all three of them are equivalent to each other. Okay, they're all the same circuit, just simplification. So here's the formal problem that I simplified to here, right? So I believe this was 8, and this one here was the 4 ohms, right? And then this final here had the 12. So they all are equivalent to each other. Really, really important to note, because it's going to come back to save us at some other point, or some other types of problems, especially when we get to the AC stuff. So now we can see that. And what I just solved for, okay, was the currents in I1. So we're going to use a different color. Yeah, that's not a different color. So let me try one more time. So over here, what we solved for is I1 and I2. Sorry, I'm running out of space here. So I1 and I2. And again, it's to be the same I1 that you have here and the same I2 that you have here. And the question is, why are I2s the same in both instances? Because they're both on the same branch. So I'm just only draw you the one branch that matters for now. So this is the 12 ohm branch, and over here can be like this. So we have here 8 ohms and the 4 ohm on that far right branch. So why is this so important? Because the current is the same here. So this is still I2 and this is still I2. So why again? Because if you have 100 resistors on a same branch, they all the same current. Why? Because this is essentially a series circuit that we're investigating right now, from that top node to the bottom node. Okay, so that's really important, which means that graphically, I didn't mean to do that, I didn't mean to use that color, but graphically, this one over here, the far node, if I may, it's going to look like this. It's going to be the 8 ohm resistor, and then it branches off like this. See if you understand this variation. This is really important. And here it is. So all 3 of these branches represent the same problem, the same currents, right? So we be more precise. So I2 is my current through the 8 ohm branch. But as you can see, is that when the 8 ohm reaches here, and again, I'm trying to show you the representation, it could split back between the 5 and the 20, and then it recombines over here to be the current of I2. Critical that you can visualize this. And boy, if you can see this now, it actually makes everything else so much easier when it comes to looking at currents across branches. So there it is. So you have the currents that get split temporarily, and then that current gets split, and then the current again rejoins back here at the bottom for all 3 scenarios. So if you're solving for the current in either the 5 ohm branch or the 20 ohm branch, well, at that point, you know, it makes sense to use another technique, right? And that other technique in this case is a couple of options, but the one that might make the most logical sense is our current division. Okay, so what was the current I2? So what we'll see here is that the current here is 0.9994 amps here, here, and here, and it temporarily splits across the 5 and the 20. It recombines here or here, and it's the same 0.944 here, right? So that's the important part, is that it recombines at some point. So which method makes sense? Again, I guess Kirchoff's current law makes sense. So if you wanted to figure out how much current across either the 5 ohm or the 20 ohm resistor, it's going to be using current division. It's going to be essentially this is how I like to do it. It's going to be I total, right? And then R total. And again, this is for the parallel pieces only. Okay, so the current total is the 0.944 amps, and my resistor total, right? So we did 20 ohms and the 5 ohms, but only the parallel piece. And what we found out before, that the 20 and the 5 makes the 4 ohms. Okay, so again, the 20 ohm resistor and the 5 ohm resistor came out to be 4 ohms. So if you look before, that's a total resistance of that parallel portion. However, the fractional piece, right, is what we're trying to solve for, and the fractional piece is going to be the following. It's going to be equals to the unknown. So say if we want to solve for the 20 ohm resistor, it's going to be 20 ohms of I of the 20. So that's a fraction of what we're trying to solve for. So if we multiply those two together, so I'm going to use my calculator here on the side. I believe this comes out to be 3.77 repeating here. So ohms times this gives me back a voltage. And then we have here I20 of the 20 ohm resistor. So then you're going to have I of the 20 ohm resistor. So I have the 20 ohm resistor is going to be 3.77 volts over 20 ohms. So let me see, using my calculator on the side again. So I get back a number. So I of the 20 ohms equals 0.188 repeating amps. Okay, and then if your question is to find the 5 ohms, you do the same as you did before. So let's try this again. So then I'll do this equation. Let me just copy and paste it first time. So copy, paste, and this time, of course, we're not solving it for the 20. We're going to solve it for the 5 ohm resistor. So this is also becomes the 5 ohm resistor. Okay, so this, of course, turns into my still the 3.77 repeating of I of the 5 the 5 ohms. So I'm going to save a little bit of time here just doing it like this. So let's see if I can do it with the calculator on the side. Divide that by 5. I get back I of the 5 will equals to 0.755 repeating amps. Okay, and hopefully that makes sense. Why again? Because if I drew the node itself, well, I don't have to redraw, it's already here. So let me copy and paste this over here so you can see it one more time. Copy, paste. So what that's our values, our solutions, we get back mathematically is that we got here 0.188 amps repeating on this side, okay? And on this side we have temporarily 0.755 amps repeating as well. More current through the lower resistor side because it's easier for the current to flow through less resistance. So if I add that to 0.55 to the plus the 1.888 repeating, we get back the 9444 that we had before. So again, so if I drew out the visual, it's going to be like this. It's going to be 0.755 amps. It's entering this bottom node over here. And then I'm going to have here the 0.188 amps, and then as we noticed before, we expect that down here it's going to be 0.944 amps back, so it checks out, right? Or it satisfies KCL as well. The sum of the currents entering are equals the sum of the currents leaving the node, and we solve that the sums nets equals 0, which is the math important part. All right, that's fantastic that we have this problem as well. Okay, so if you made it this far, we have our last problem here, which you can think of as bonus to see if we understand all this. And as you can imagine now, we're looking at a 3-mesh problem. So if we were to approach this problem, our goal, of course, is to write the KBL equation for it. So let's go ahead and do what we've done before. And we're going to first identify those 3 loops. Doesn't matter which one you name them, but I'll probably, let's see here, I'll just call this one here I1. All right, so I'm going to call them I1, I2, I3 for convenience. So this is I2. And then finally here, I3. And I'll do what I did before, which is write down their equations for each of those loops. And the idea after that is then I'll solve, okay? So let's go through each loop and see how do we get that. So our first one, give it a name, of course. Loop number 1's equation is going to be minus 7 volts plus 1. I'm in loop 1, so I'm 1 minus I2 plus 6 volts plus 2, still in I1. I1 minus I3, all of that equals to 0. Okay, I can simplify that as well. So, you know, just trying to simplify this as best as we can. So let me just write it all out for you, and you can hopefully get the idea of this as I go through it, so you can see how this would play out. Okay, and again, let me just doing most of the stuff live so you have a better sense of how this works. Okay, so now I'm going to put together all of my like terms, hopefully not make too many algebraic mistakes, which again, with circuits, unfortunately, mistakes can happen because you're writing quite a few digits together. Okay, and then we'll hopefully solve. All right, so just like that, oh sorry, put algebra there, so moving the 1 volt over, right? So just like that, we're able to have our first equation simplified for loop number 1. Okay, and now we're going to repeat that for loop number 2 and loop number 3, and hopefully we'll have 3 equations, and then your anticipation to tell you that we should have 3 unknowns. So now for loop 2, I'm going to do the same. So I'm in loop 2. It's going to be, I like to start, say, here, 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 and here. And of course, the previous problem wasn't obvious. I was doing this. I'm just going around this entire thing. Okay. All right, so for loop 2, I'm in loop 2 now. It says 1 ohms. And because I'm in loop 2, I put I2 first. I2 minus I1 plus 2i2 because the 2 ohm resistor is not being affected by any other mesh current. And finally it's plus 3, and I'm in loop 2. I2 minus I3's current flow equals 0. Then I have an equation for loop 2. So I'll distribute this one again with you so you can kind of get the hang of it. And also you can see how I'm troubleshooting this problem. And then we'll solve. So at this point, all of our I2 terms are over here. One I1 and one I3 term left. So I have here minus I1, 2, 5. Just give us back a positive 6I2 minus 3I3 equals 0. So that is our second equation. Okay, and then finally, let me copy and paste this one last time. So if I copy this, paste this, and I paste this over here, I can write down my loop number 3 equation. And again, let me see if I can erase that. Yeah, I guess I can. So if this time I'm going to go from this bottom edge, A, B, C, and D. Okay, always start in the bottom left hand quarter. Again, if you do things the same way all the time, you're less likely to make mistakes. I'm in loop 3, so it'll be I3 minus I1, right? Then I'm entering the negative terminal of the 6 volts, so it's minus 6V. Then I'm 3 ohms. I'm still in loop 3, so it's I3, and I'm going against I2's current for that resistor. The 1 ohm is isolated, it's not affected by anything else. So I just put down 1I3 equals 0. Okay. And I distribute this out and I solve. So I'm going to be left with something like this. Okay. And I try to simplify this as well. And I solve. Okay, so you have the minus, let's see, minus 2I1. Then I2 terms only 1 I2 looks like, so it's 3 I2. And there's 3 of these, so it's 3 plus 2 plus 1, so it gives me back positive 6 I3. If I move the negative 6 volts from the left side to the right, I get back positive 6 volts. Okay, and just like that, I have my 3 equations. So then I can summarize this now. So if I summarize and I solve, so if I summarize them, I'm essentially going to just copy each one of my loop equations, right? And then we're on our way to getting this problem done, which is really exciting. Okay, so that's equation 1. And again, the idea is to stay as organized as possible. Try not to just change your pattern very often. Just stick to one method, and if you enjoy it, particularly this method, of course, I would recommend you stick with it the entire way, because I can do all these problems this way. I can technically go clockwise and counterclockwise, but it's not consistent, and I appreciate consistency when I do any types of problems. Okay, so here's EQ1, EQ2, and then finally EQ3. All right. So I have all of my equations, and now I have to solve. So as you saw before, certainly we can consider doing a substitution method, and we can do that. It might take us a while, but at this point it makes a lot more sense, because remember, I'm just doing an eyeball test to ensure, because nothing over here cancels out all the I1's terms or all the I2 terms right off the bat, or the I3 terms right off the bat. So we'd have to manipulate this for a while. But what we've learned is that there's other techniques, and a really practical one is, of course, Kramer's rule, that could help us solve this. So the idea is that we're going to solve this and create a matrices of this, and then we can go ahead and solve. Okay. So if you're unfamiliar, you can take a look at my other video, or just, take a look. I'll put a separate video up soon about just doing basic math equations with Cramer's rules. But I did show how to do a 2x2 and a 3x3 in a prior video as well. So the idea again is I could convert this entire thing into a matrix and then solve for its determinants using Cramer's rules. So I'm gonna be left with this. Okay, so I took the terms and I created a matrix to solve for its determinant of this 3x3 matrices. Okay, and we can go ahead and solve for this, and as long as we're consistent with the algebra, we should be in reasonable shape. Okay, so where do we go from here is the strategy. So if you would like, I can go over this in detail. Let's say why not. So let's just copy and paste this. You can see it all together. And what I'm going to do is graphically show you how this works in this form first. Okay, so let's try this out. I'm going to try something. So the first thing we can do is we can solve for using Cramer's rule. And essentially what I'm going to be doing is just simple cross multiplication. So I'm going to show you what I'm cross multiplying so you have an idea of this. And then you can certainly try this on your own. So when you cross multiply this here, I'm going to take here the portion I crossed out, which is the 3, right? And I'm going to develop a new 2x2 matrix. 2x2 matrix so much easier. And that 2x2 matrix that's left is a 6 minus 3 minus 3 and the 6. Okay, and where did I get that from? Is that here are my 4 remaining numbers. 6 minus 3 minus 3, 6. And the same strategy for the next one here. It's going to be minus 1. And then I'm going to be including this 2x2 matrix, minus 1, minus 2, minus 3, and 6. And then finally, the last one is going to be minus 2 and multiply by a 2x2 matrix. And the 2x2 matrix will be minus 1, minus 2, 6, and minus 3. Again, this is just a strategy to doing system of equations. So what we've learned from using the system of equations is going to be we're adding this one. Sorry, take that back. So we're going to do that, and we're going to subtract, put this in brackets, this entire thing, right? Then we're going to add this term here. And we're going to solve for the determinant of this 3x3 matrix. Okay, and in order to solve for that, we're essentially cross-multiplying these variables and then multiplying it by this factoring outside. So if we do that, it's going to be the following. It's going to be 6 times it by 6 minus negative 3 times it by minus 3. Then we're going to multiply that by 3. So it's 18 minus 9, right? Times it by 3 is what we're left with, because negative 3 times by negative 3 gives it back a positive 9. 18 minus 9, so we get back our 9. 9 times 3 gives us back the 27 for this first portion, right? And then the next one you do the same, so we're going to be left with negative 1 times it by minus 1 times it by 6 minus negative 2 times it by minus 3. Okay, and as long as I can do algebra, hopefully I don't make too many mistakes, but minus 6 minus positive 6, right? This becomes positive negative. So this comes out to be negative 12 times it by minus 1, okay? And that gives it back a positive 12. Remember, there's a big minus sign in front of this as well. So far we're going to have 27 minus 12, okay? Because my determinant. And then finally the last piece. So the last piece of this is going to be minus 2 times it by minus 1 times it by minus 3 minus 6 times it by minus 2, close brackets. So again, this gives us back positive 3 minus minus 12 times it by minus 2 plus a positive. So this comes out to be 15, and then this turns out to be minus 2. So it gives us back minus 30 back, if I did my algebra correctly. All right. So hopefully I did. I'm just double checking myself for a quick moment to make sure I didn't make any silly algebra mistakes. So I tragically made a silly mistake, so please correct this. I'm going too fast. So this is not a 3 over here, right? It's 6 times 6. I think I said it, but I didn't write it. So I'm using a different color. Whenever I make mistakes like the switch it up, so this is actually 36. Okay, that makes more sense. So if we did that, so then that leaves us with the 27 times it by 3, so it's actually incorrect, right? So this comes out to be, let's see here, so it becomes 81 is actually the correct answer here. So it's gonna be 81 minus 12 minus 30, and that gives our answer of our determinant to be 39. Okay, so that's how you do that. And apologies for the typo, but it's going to happen occasionally. Okay, so now that we have that, our objective, of course, is to solve for I1, I2, and I3. And in order to solve for I1, I2, I3, the next step, of course, is to take, say if we wanted to solve for I1. So let me just do this here. I'm going to copy this to help us out. So if we wanted to solve for I1, so this is I1, well, equals 2. So in that case, remember our solution is 1, 0, and 6 volts. So based on Kramer's rule, right? So based on Kramer's rule, it's going to, now I replace that with 1, 0, 6. And then I put in, and I keep everything else the same. So I put minus 1, 6, minus 3, minus 2, minus 3, positive 6. It's going to be my determinant, and all of that over D will equals to I1, okay? So that is what the solution of I1 is going to look like. And I2 is going to be similar. So let me copy and paste hopefully a little more efficiently this time. So let me try this variation. So if I wanted to solve for I2 is going to equals this. And so I replace this here, cut it, and I put here the 1, 0, 6 in its place, and I divide all of that by our determinant, D. It gives us back I2. And then I do that one more time. Let's see here. So then finally over here, and now I remove this row. And so cut that, and then I put this in its place. And I put over D, and now I get back my values for I3. Okay, so that's how you solve these things. If I want to solve for I1, I2, I3, it looks like that. I don't think we have time to do all of them, but let's at least try I1, and it should become a little more automatic when you do this on your own. So let's just quickly try this out. So we're going to do what we did before. So I'm going to have here, copy and paste, make it easier. Paste that. Okay, so what we're looking at is that to solve for this, we're going to do what we did earlier. We're going to do 1, and we're going to multiply that 1 by the 2 by 2 matrix. I'm going to save time by writing in this form now. So you saw it before. Then subtracted from our second term, and this time it'll be 0, 6, minus 3, and 6. Okay, and then I'm going to add it to the minus 2, and that minus 2 is going to be 0, 6, let's see here, 6, and minus 3. Okay, so hopefully this is not too bad, and this is how it looks like to solve. for this numerator piece here. So this time I'll hopefully make less algebra mistakes. It'll be 6 times 6 is 36 minus negative 3 times by negative 3 gives it back a positive 9 times it by 1. The next term, subtract it from the minus 1, and this time 0 times 6 is 0, so it'll be 0, so it'll be minus 6 times it by minus 3. So that's minus 18, and this is going to be an algebra craze, but let's just see if we can make sure we don't make any silly mistakes here. So get back minus 18 times by minus gives back positive, so you have positive 18. And then now we're hopefully getting somewhere, and this one here reduces itself back to 27. And finally the last term, 0 times by minus 3 gives back 0 minus 6 times 6, right, which brings us this into the 36, and the 36 times by the minus 2, right, let me put it this way so it's a more formal, so that should give us back a positive number. Okay, so what we should get back is that we should get back positive 72 if I didn't make any algebra mistakes, which I hope I didn't. Okay, so now that we did that, we combine all these terms. I'm sorry, I'm just typing away to do these problems live. So I get back an 81. Hopefully that's correct this time. So if I wanted to find out the current of this, so let's see, hold on, let me triple check my math here. The only thing I'm concerned about, of course, is making sure that I have my signs correct. So when you're going a little bit fast, you make some silly mistakes. So it appears I made an algebra mistake again. So I'm just saying, I knew this was going to be a little bit of a mess here. So I'll just revisit that one quick second. So what it should be, right, is that this should be negative 3 times by minus 6, give back minus 18, right? So put this over here, minus 18. Minus 18 times it by a minus 1 gives back a positive 18, and then a positive 18 with the 9. Okay, so, I mean with the negative sign, right? So let's double check that. Actually, I'll say it one more time. I think I'm saying it too quickly. So minus 3 times by 6 gives minus 18 with a minus sign in front of it gives it back positive 18. Times it by the negative 1 gives us back minus 18. So this is how it should have looked like actually, right? So just double check that. So it looks more along the lines of this. So this then becomes 27 minus 18 plus 72 is the correct form. Sorry, I went too fast before. So if we did that, then this becomes plus a positive, right? So it becomes plus a positive with the algebra. So then we're going to be left with 27 plus 18 plus 72, and we get back 117. So if we wanted to solve this problem, it's going to look like this. It's going to be I1 is going to equals to, let's see here, it's going to equals to 117 over D, where the determinant we ended up getting it to be 39. So it's going to be all of that over 39. And it's going to be 117 divided by 39. And that gives us I1 equals to 3 amps. Thankfully, that looks good. All right, so that's how you do that one. Okay, so sorry about the negative piece here, but I knew I went a little bit too fast. It was a mouthful, but just be cautious with that, what I just did again. So again, minus 3, minus 6, minus 18. Minus 18 times it by minus 1. Sorry, a negative 6 times it by, these two terms makes it minus 18. And then again, times it by another negative. Okay, so it becomes kind of kind of wild, but you're left with a minus 18 overall, and then you combine it the negative. I leave the negative sign outside. I went too quickly before, and then when you simplify, you get back to 117. All right, that's just a little bit of a tongue twister, but hopefully you get the idea. We can certainly try I2 as well, but I2 is going to be the same approach, and so will I3. And then that should be able to give you a good feel for how to solve this problem. And I2 will be easier this time because there's no negative 1, it's just be positive 1. So you know what, we've come this far, might as well go with it. Let's try this for the I2 as well and see what we get. So I2 is going to look like this. So I'm going to write down quickly these determinants. So I mean to set up the matrix. So we're going to have here 3, 0, 6, minus 3, 6. Then it's going to be subtracted from 1 times it by minus 1, minus 2, minus 3, 6, plus, then it's going to be minus 2, and then it's going to be minus 2, then it'll be minus 1, minus 2, 1, and 0. Okay, just eyeball that quickly to make sure to make any silly mistakes again. So 0, 6, minus 3. I'm going to move this 1 a little bit because it seems so low, it's throwing my eyes off. Okay, so then it's going to be 0, 6, minus 3, 6, and then the next one would be 1, minus 1. Okay, so this looks good as far as a quick eyeball test is concerned. So this is not, yes, this is also, this is bad. We'll fix that one here. Okay, so now that I did that, we should be in better shape, okay, to solve for this. All right, and again, just double check Kramer's rule so you can see this more clearly. So 0 times it by 6 gives me back 0. Then this gives me minus 18 times it by 3. Okay. And then the next term is going to be negative 1 times it by 6, which gives me back, let me just write this one out because I don't want to confuse myself again. And then it'll be minus 2 times it by minus 3. Times it by 1. I'm just going to write it out now. I'm rushing, that's because of sake of time, but let me just show you all the steps so I don't make any mistakes. And you can see it more clearly. Okay, so this is what we expect. And again, this will be a minus sign between these two over here. Based on Kramer's rule and explanation, so check that one out. And this one's going to be minus 1 times it by 6 minus 2 times it by 0. Okay. Again, I'm going to try to be neat. And all that's going to be multiplied by minus 2. Okay. So let's see what we get here. So positive 6 is going to be minus 6 minus 6 again. Okay. So I make this plus a minus. So minus 12 here. Times it by 1, of course, give me back 1. So a minus 12 minus 18 times it by 3, which gives it back a minus 54. Okay. And finally, the last term here, we have the minus 6 minus 0 again. So this one would be 6 times it by minus 2 to get back minus 12. Oh my gosh. Hopefully no silly algebra mistakes again. So when we combine that, you know, we expect this to be this. Let me just plug everything into my calculator to just ensure that I did it right. I'm just doing this quickly. So what we should get back here is the minus 54 here. And let's see. Just triple check something here. Okay, so after looking at it, I still made an algebraic mistake, so sorry. So a negative times a negative here is actually a positive, right? So this is not correct, so please correct that. So positive 12. And over here, 6 times minus 3 is minus 18, but I forgot the minus 18 times it by this minus sign in front of it, right? So a negative, negative, so that makes this actually positive 18, right? So it makes this a positive 54. So sorry about that. So our final answer for this entire thing is going to be equals to 54 plus 12 plus 12. So let's see here. So then we get back equals to 78. And so our answer for this problem is hopefully, let's see here. So now I'm going to copy and paste this. So our answer is going to be, for I2, it's going to equals to 78 over 39. So we get back I2 equals to 2 amps. Okay, finally. That's better. So again, be cautious of the algebra. Don't, sometimes it's hard for me to type and talk, or talk and type, and to calculate. So that's how you get these answers. You get back to 2 amps. All right, and then finally there's an I3 somewhere, right? And the I3's approach is going to be over here. So if the I3, we're going to do the same thing, and this time pray with no algebra mistakes. I'm going to use another color for some better odds here. So I'm going to do 3, and then it's going to be 3, 6, minus 3, 0, and 6. Move this up again because it's a little bit low for my eyes. And then I'm going to do subtracted from minus 1. And then this time it's going to be here minus 1, minus 2, 0, and 6. And then finally I'm going to do 1. And that 1 is going to be times by, it's going to be minus 1, minus 2, 6, and minus 3. Okay, so 6 times 6 is definitely 36 minus 0, right? So this one's going to be 36 times it by 3. So this time over here is going to be cross multiplication. So it's going to be minus 1 times it by 6. Minus 2 times 0 gives me back 0. Okay, so this is going to come out to be minus 6. Multiply that by the minus 1. Gives it back a positive 6. So it's going to be minus a positive 6. And then 36 times 3, that's going to give us back the 108 minus 6. Okay. And then our last term over here is going to be minus 1 times it by minus 3 minus 2 times it by 6. Okay, and then all that multiplied by the number 1. So it's going to give us back a positive 3 minus a minus 12. Okay, because plus a positive, so it becomes 15. Times it by 1 is still 15, so I get a positive 15 back. Okay, so let's hope we did this right. It's going to be 108. So let's see here. So I get the 117, okay? And then the 117, so our final answer for this one, if we did the algebra right, is going to be this, okay? So the equals to the 117 over the 39, and that gives us back 3 amps. So we're all done. So again, this is a worksheet review or / midnight work efforts to try to get these problems out. So we're able to solve for I1, I2, and I3 using this matrix approach. So you have here 3 amps, and I1, which I've forgotten already, I2 is 2 amps, and I1 is 3. So 3 and 2. Okay, so then this would be 3 amps, and then I2 is going to equals to 2 amps. And we are done. And to do a check on your own, what you'll do is that you can certainly plug in these values into your KVL equations. Try it out to make sure that the loop equations hold true, and if they did, then you know you've done everything correctly. You could also do a quick simulation of this problem as well to see if it's okay. So let me again show you how this looks like. Since you've come this far, you would then plug in your values here or use your loop equation. So let me just copy this entire thing so you can see them more clear. I'll just copy this equation since it's right in front of me, and then you can just plug everything back in. and hopefully everything that's 0, which I'm sure it will, and then you put them all back in, and then you're free to solve and try this out. So here's a loop 2 equation. So if we plugged in our variables as our part of our check, right? So for our check, what we should do here, we have our just plugging our numbers. So our 2 amps minus our 3 amps plus 2 times 2 amps plus 3 times 2 amps minus 3 amps hopefully equals to some value that's 0. So you get minus 1 plus because again we're multiplying it by 1, so it makes it to volts, right? So then that becomes 4 volts, and then here we have back plus a minus 2 amps minus 3 amps because minus 1, so then that becomes back minus 3 volts. So thankfully minus 3 plus 4 volts equals to 0 volts, so our check holds true, and we proved that the KVL worked and that we didn't make an silly algebra mistakes anywhere, and we've done it. So again, this is a midnight worksheet challenge. You have an idea of how to do these problems consecutively. I try to do it as live as possible so you get a sense of how I potentially can make mistakes. If I potentially made a mistake, you'll see where potentially you would have made a mistake. And it's just practice and keeping books organizing, try not to rush, and taking your time to solve this, and you should be good to go. All right, so that concludes the video. Hope you learned something. If you did, please continue to watch the others.